Hello everyone. In this video, we are going to discuss Clausius theorem or Clausius inequality. The Clausius theorem states that for any closed process or cyclic process, the integral on a closed path dq over capital T at absolute temperature is less than or equal to 0. For any cyclic process means it has two parts. The process can be reversible cyclic or irreversible cyclic. If the process is reversible cyclic, then the integral on closed path dq over capital T at absolute temperature is equal to 0. But if the process is irreversible cyclic, then integral on closed path dq over capital T is less than 0. In this video, we are going to prove for the reversible cyclic process, the closed integral dq over capital T is equal to 0. And in next video, we will discuss the for irreversible cyclic process, the closed integral dq over capital T is less than 0. Now, first of all, we have to consider the reversible cyclic process, and the reversible cyclic process is Carnot cycle. Now, consider the Carnot cycle. As we know that the Carnot cycle consists of two isothermal process and two adiabatic process. The Carnot cycle consists of two isothermal and two adiabatic processes. If we draw this PV diagram for the Carnot cycle, here we draw the pressure, here we draw the volume. The Carnot cycle from state A to state B, for example, it's a isothermal process A to B, and then B to C for the adiabatic process, then C to D, and then D to A. These are four processes, two isothermal and two adiabatic. First of all, consider two isothermal processes. For isothermal processes, we know that the first law of thermodynamics says that the dq is equal to du plus dw, the work done. As for example, the QH heat enters in this system while process goes from A to B, because it is an expansion process A to B, and the expansion process says that the temperature of the system may decrease, and if we have to constant the temperature of this system, the heat must be entered in the system so that the temperature of the system remains constant. That's why the QH heat enters into the system, and the internal energy of the system goes to 0, because the change in internal energy is 0. The internal energy only depends upon the temperature, and temperature of the isothermal process remains constant, and we can say that the dq heat entering to the system is equal to the work done dw, and dq is equal to p dv. Now consider the isothermal process from A to B. Then the pressure of the system can be written as the dq is equal to pressure is equal to, from the ideal gas equation, PV is equal to nRT. It is equal to nRT and divided by V and dV. As the temperature at this point A to B, here the temperature is TH, and the temperature at point is also TH, because the pressure and the volume is changing but the temperature remains constant. Temperature is TH, that's why we write this TH. And if we integrate the both sides, then we will get the QH entering to the system is equal to nR. TH is the constant. We integrate the volume 1 over V and dV. We will get the NR TH, the volume goes from VA to VB, and the limits is goes from A to B. Then we will get the natural log of V, the upper limit B, and divide by lower limit VA. QH, the entering heat to the system is equal to QH is equal to nRTH, natural log of VB over VA. It is our equation 1. Now consider the another isothermal process which goes from C to D, and in this process the compression is taking place because the volume is decreasing, and then due to compression the temperature of the system might increase, but we have to consider isothermal process to constant the temperature of the system. The heat must leave from the system, which is QL heat. And for this isothermal process, which is C to D take place, the adiabatic process is taken place from B to C, and due to this adiabatic expansion, the temperature of the system have been decreased, and now the temperature is TL at point C, and the C to D is also the temperature is TL, because the C to D process is isothermal, the temperature is not decreasing. Now from this integral from C to D, we write this expression integral dq is equal to nRTL and integral of V and dV. But the limits of this will change from C to D, and the temperature is also changed from this equation. Here the temperature is TH, now the temperature will become TL. If we integrate both sides, we will get here the QL, heat leaving from the system, is equal to minus, because minus is because the heat is leaving from the system, then we will this heat taken as negative nRTL. Now the integration of this 1 over V, sorry, here is 1 over V dV, it will become the natural log of upper limit VD over Vc. If we write this negative to the power of the natural log, then this order will be reversed, and the QL will be equal to nRTL, the natural log of Vc over Vd. And this is our equation 2. If we divide both equations, equation 1 and equation 2, we will get the QH over QL is equal to, the QH is nRTH, the natural log of VB over VA, and here the QL is nRTL, the natural log of Vc over Vd. The nR will be cancelled out, and we will left with this equation as QH over QL is equal to TH, natural log of VB over VA, and divided by the TL, natural log of Vc over Vd. Here is our equation for example A. Now consider the two adiabatic processes. Two adiabatic processes goes from, the first adiabatic process goes from B to C, and the temperature at B, we know that the temperature at B is TH, and the temperature at C now become the TL. The other second adiabatic process goes from D to A, and the temperature at D is TL, and the temperature at A is TH. Now we know that according to the adiabatic process, the PV gamma is equal to constant, and if the PV gamma is equal to constant, it means that the pressure at B is multiplied, the volume at B power gamma is equal to the pressure at C The volume at C, the power gamma, are equal. Now putting the values of pressure at B and the pressure at C, we will get the pressure at B is nRTH over V at point B. Now power gamma and V power gamma, VB power gamma is equal to nRTL divided by the volume at C, because we are putting the values of PC, the pressure at C point, the volume will be VC, and now the VC power gamma. Now rewrite this expression, nR and nR from the both sides will be the cancel out, and we will get the TH VB power gamma minus 1 is equal to TL VC power gamma minus 1. And now this is our equation number 3. Now consider the second adiabatic process which goes from D to A, and we can write this expression. Similarly, the temperature TL and VD power gamma minus 1 is equal to TH and VA power gamma minus 1, which is our equation number 4. If we divide these both equations 3 and 4, we will get, if we divide these both equations, we will get now equation 3, write this equation 3, TH and VB power gamma minus 1, and divided by this term that of equation 4, TH VA, the TH VA power gamma minus 1 is equal to, now the right hand side of equation 3, TL VC power gamma minus 1 divided by left hand side of equation 4 this side, and TL VD power gamma minus 1. TH and TH will be cancelled out, and here from right hand side the TL and TL will be the cancel out. Then we will left with the equation VB over VA is equal to VC over VD. As the gamma minus 1 power is for the both sides, the power gamma minus 1 will be cancelled out, and we will left with this equation VB over VA is equal to VC over VD. If we plug this value in equation A, plug the values in equation A, the VB over VA is equal to VC over VD. From this equation, the QH over QL is equal to TH over TL, as the natural log of VB over VA, natural log of VB over VA, and the natural log of this VC over VD is also equal to VB over VA, and the both terms, natural log of terms, will be cancelled out, and we will get the QH over QL is equal to TH over TL, which we used in our Carnot's engine's efficiency. As Carnot's engine efficiency was 1 minus QL over QH, and we write this efficiency as the efficiency is equal to 1 minus ratio of heat is equal to the ratio of temperatures, which TL over TH. And now we have proved that the QH over QL is equal to TH over TL. We can write this expression as this: QH over TH is equal to QL over TL. We replace these two terms. And now we can write this expression, the QH over QL minus, QH over TH minus QL over TL is equal to 0. And if we write this expression, integral of dq over absolute temperature for a closed cyclic process is equal to 0, which is our desired form for closed cyclic process, Clausius inequality. The first part of Clausius inequality we have done in this video. The next video we will discuss the closed integral dq over capital T is less than 0 for irreversible. And here the dq is for reversible cyclic process, and we will discuss the irreversible cyclic process in next video. Thanks for watching.